Hello, this is part two in the video presentation on the Urysohn metrization theorem. In this video, I'm going to go through step one of the proof of the Urysohn metrization theorem, and I'm going to go into very great detail. So if we go back to what step one is, so we see that step one, show there exists a countable collection of continuous functions, Fn, from x to the closed interval 0, 1, such that given any point x naught of x and any neighborhood u of x naught, there is an index n such that Fn of x naught is positive and Fn of x is 0 for x not in u. So we're going to need some preliminary results in order to prove this. So the first result is that if we have a space which is both regular and countable, that space is a normal space. So we're going to take that for granted. The next thing we're going to take for granted is the Urysohn lemma. And I'm not going to state the Urysohn lemma in its exact form, but I'm going to state it in a form which is going to be useful for us in this proof. So let's say we had a basis element Bn, and then we took the closure. You can see that in the figure. It's the black black shape in the middle. And it's inside of another basis element, Bm. And then you see outside of that is everything, the whole space, x take away B sub m. So you have this closed set, the closure of the basis element B sub n, and then you have another closed set, x take away the basis element B sub m. So according to the Urysohn lemma, we would have a continuous function f from x to the closed interval 0, 1, such that the image of the closure of B sub n is equal to 1, and the image of x take away B sub m is 0. So this is going to be important. This is how we're going to construct, we're going to get our collection of continuous functions which fulfill the properties that we discussed. The next result that we need is that given a regular space, so this figure is supposed to represent a regular space, and you see there's a point x naught in the middle there, and this point x naught is inside this blue open set. It's actually a blue basis element, Bm. So we have a blue basis element, Bm, and that's obviously an open set. So given regularity, we can get another basis element, B sub n, take the closure of that, and the closure of that is going to be a subset of the basis element Bm. And this is also going to be important, as we will see. And that is, this result is given the fact that the space is regular. So now we're going to get our collection of continuous functions. So we let Bn be a countable basis of x. As you remember, the set of the topological space X has a countable basis. So Bn is that countable basis. So for each pair of indices, n and m, for which the closure of Bn is a subset of Bm, we apply the Urysohn lemma to get a function g sub n comma m from x to the closed interval 0, 1, such that the function applied to Bn, the closure of Bn is 1, and the image of the function applied to x take away B sub m is 0, and that is following this result of the Urysohn lemma. So this collection of functions is going to fulfill our requirements. If we go back to our requirements of what this collection of functions has to do, it has to be that given any point x naught of x and any neighborhood u of x naught, there is an index n such that fn of x naught is positive and fn of x is 0 for x naught and u. Okay, so I'm going to go through, given an arbitrary point x naught and an arbitrary neighborhood u of x naught, what it would look like, and basically show the proof visually. So if we get a topological space, this square is going to represent our topological space. And we have a point x naught. That's just, I'm going to draw a point. We have a open set and neighborhood of, let me make that a little bit nicer. We have a neighborhood u of the point x naught. So therefore, given our countable basis, we can choose a basis element bm. And I'll do that in orange. We can choose a basis element bn, which includes the point x naught, which is a subset of u. So this is bm. And then, because of regularity, because of our previous result, we can choose another basis element, bn. And I'll do this in black because it's going to end up being a closed set. We take this bn, we take the closure, and it's a subset of bm. All right, so now we apply the Urysohn lemma. So the Urysohn lemma would give us a function g n m such that g n m applied to b sub n closure is equal to 1, and g n m applied to x take away b sub m is equal to 0. So this function fulfills our requirement because given any neighborhood u of x naught, we see that GNM of x naught is equal to 1, and GNM of all x outside of u is going to be equal to 0, and that's what we wanted. So given any arbitrary point x naught and any arbitrary open set u, we get this sort of function. So now we see we have this collection of functions GNM, and these functions are indexed by a subset of z plus cross z plus, which is a countable subset. So therefore, this whole collection is countable. And that is part one. That is part one of this proof, that we have a collection of countable functions, of countable continuous functions, from x to the closed interval 0, 1, such that given any point x naught of x in any neighborhood u of x naught, there's an index n such that fn of x naught is positive and fn of x is 0 for x outside of U. It vanishes outside of U, the open set U. Okay, that was part 1. In the next video, I'm going to go through part 2 of the proof.